For our next speaker, we will have Alain Brenzikofer, software engineer at Integritee. He will get us to the world of confidential data handling using trusted execution environments. Welcome, Alain. I'll let you take it from here.
All right. Thanks a lot for the intro. Yeah, it's good to be back here at Sub0. It's a pleasure. The story actually started over 2 years ago when we got the grant from the Web3 Foundation to develop Substrate. Substrate was meant to be tooling for Substrate developers, and now today I'm presenting Integritee. Integritee is a rebranded Substrate, but it also is a platform which is aiming to become a parachain. So it's also a platform to deploy to for Substrate developers. And I will tell you a bit more about this during this workshop, what we can do for you, how you can do it, and what we are about in general. So we have we live in a world where data is very important, very valuable, especially personal data. And there is an increasing pressure on protecting this personal data. And so both from the user side, there's from the community, there's a pressure, but also the regulators are catching up. And for example, in Europe, we have the GDPR, which is a very strict law about how companies may treat personal data. And well, there is this one solution that might help with data ownership, might be an answer to this, but well, there's the fundamental problem that blockchains are transparent, and so what we would like to propose is a solution for the three big challenges of blockchain, which we see as being confidentiality, scalability, and interoperability. Now, what do we mean with that? Confidentiality, I think, yeah, well, this is, you don't share more information than what is actually needed to take out some action, and that should be the real minimum. We have, as I mentioned, GDPR, which is in a certain conflict with blockchain because of the right for deletion, for example, and because data may not be linkable in any sense. And blockchain is, by design, in a conflict with this requirement. Scalability is, well, still a big topic for blockchain. So imagine CryptoKitties. So we have two dApps running on blockchains, and you are not CryptoKitty, you are the other one. And CryptoKitty goes through the roof and gets very popular. Take, well, Uniswap or whatever example. And your dApp will be suffering because the other one needs so many resources and fees go through the roof. So we would like to decouple that for different dApps. And then there's interoperability. So far, blockchains are mostly golden cages. So as long as you stay on the inside of a blockchain, everything is perfect. All the rules are abided to, and nothing to worry about, no trust needed. But actually, we live in a physical world. We have different systems, a heterogeneous system. And we also want to not only interoperate with other blockchains, but also with legacy Web2, REST APIs, whatever. Now, what we do as to enable or to tackle these three problems, we combine a public ledger, Polkadot, or Kusama, with trusted execution environments. And that is what Integritee is about. So what are trusted execution environments for those that are not familiar with that? Trusted execution environments are a hardware design where you can execute a process in isolation from the operating system. That means you can execute a piece of code. The administrator of the machine can stop the code or start the code, but it cannot see the data which is processed by that code, and it cannot change the code. And that's the guarantee, the hardware guarantee that these devices give us. Now, in the blockchain sense, usually the infrastructure is run by someone else than ourselves. So how can these infrastructure operators convince us, users, that they are actually executing some piece of code on a real, genuine, trusted execution environment? That's what remote attestation is about. So the manufacturer of the TE device, in our case, this is Intel, so we use Intel SGX. They can remotely verify that a piece of hardware is genuine, and they can also measure the code, the binary which is here, so that the hash of the binary. Now, if we combine this idea with open source code, so we have some piece of open source code, we can deterministically build that code. That means we know the hash of the binary which has to be executed corresponding to that code, pretty much as the runtime updates of Polkadot and Kusama are done now. You can execute that on a trusted execution environment, and Intel the manufacturer, will measure that and give you a certificate, a report about that device and what it is running. So now, this for itself doesn't need blockchain, but there is an issue here. You need a commercial license with Intel in order to obtain these remote attestation certificates. And if, as a user, it is not very convenient to check for these certificates. And if we think of hardware diversification, actually a blockchain would be the perfect place to be the root of trust of such hardware credentials, so that when the piece of hardware leaves the fab, it either has some physically unclonable function on it, or it has some fuses burned, whatever, and you can write that fingerprint in the blockchain. Then you don't even need attestation services at all, and that's where we're, well, on the long run, will be heading, even if today we work with Intel SGX. Now, what we can provide with that is really this public registry, which will be the Integritee parachain, where everyone can either run a TE and send their remote attestation to be verified, and so get public auditability, or as a user, you just check that registry to look up the URL of a service which is running in a TE that you want to talk to, and the authentication credentials. Now, what we can deliver with this system is we can have a second layer protocol, which I will explain more about it, which gives you scalability. You have very good interoperability, because you can have non-repudiation as kind of an oracle. So you have a TE looking up or querying some Web 2 interface, and so you actually know that at that time this was the content of such and such web page, or the response of such and such API. It's all verifiable, because it all ends up on the blockchain with some kind of proof. It's very accessible to developers, especially here in the Substrate ecosystem. I will tell you more about this. And what is a bit special about the Integritee parachain is that our fee model actually doesn't intervene with the teams who build on top of our platforms. So we don't oppose our token to the teams on top. We just have a stable fee, stable with regards to the US dollar that we charge. We charge it in tokens, but we adjust it. And this is especially important because we also focus on bringing enterprise use cases to public blockchains, and they need predictable fees, and so we answer that with such a stable fee economy. And the deployment is also something of a USP here, because you can choose to be permissioned or unpermissioned with your sidechain, with your layer 2 solution. Also here, I will tell you a bit more in a minute. Now, how do we actually do this second layer off-chain computation? So I already said we want to be confidential. So let's focus on confidentiality first. We have some kind of a process running in our TE enclave. It's just some state transition function. A user would like to invoke one of these functions, like transfer funds from A to B, but doesn't want the world to know about this. So we have the first solution to this that we have is indirect invocation with off-chain workers. So we have the TE hooked up with the Integritee parachain. The user sends an encrypted call to the Integritee parachain as an extrinsic. Now, this is just an opaque payload which is forwarded with every new block to the enclave, and the enclave has the decryption key. So actually the user first has to, we call it the shielding key. So the user first looks up the shielding key of that enclave, encrypts the call, sends it to the blockchain forwards it to the enclave. And the enclave can decrypt it and can execute it on encrypted state. So the encrypted state is also an important thing here, because the enclave by itself is stateless, but it has the capability of storing data on the disk in a sealed manner, in a way that only the same enclave can later read it again. So even if you shut down the enclave and you start it again, it will be able to read that storage, but only the same hash, the same code. Okay, now this is indirect invocation, and this is what we already demonstrated 2 years ago. That is nice for confidentiality, but not so much for scalability, because you still have to send each and every single state transition function to the blockchain, and you even increase the size of the transaction. So the scalability is actually inferior to pure native blockchain transactions. But still, for use cases that don't have so much throughput and maybe a higher computational complexity, this is a very interesting approach. Now, now it gets really interesting, and that's something that we were able to develop with the help of a Polkadot treasury grant, actually, and that's the sidechains validated by trusted execution environments. Now, consensus protocols are something which is basically motivated by the fact that different validators don't trust each other. That's what blockchain is about. That's why we have all these consensus protocols with kind of game theory, whatever, economic design around it. Now, if we have trusted execution environments, that actually means that we accept the trust model that these devices are trusted, so the validators can trust each other. And this greatly simplifies the consensus protocol, because now we don't need every validator to execute all the transactions again to see if it's correct, because it's enough if validators can mutually remote attest each other that they know the other is genuine and running the same code as I am, and that's fine. So one can execute and just broadcast the state diff to the others, and they will include it, they will accept it. So that's why we can reach sub-second block times on the second layer. So we really built sidechains which are independent of each other and which just need the Integritee parachain as a finality layer where they can commit their block hashes to get finality. Yeah, basically, because forks can still happen due to networking reasons. So we need some kind of a consolidation layer, and that's the parachain. So here is how this works. We actually have the parachain, which produces a new block every, well, today 12 seconds. And we have two sidechain validators. Well, kind of a little word game. We call them validators, so you don't confuse them with the layer one. And there is no need to have many of these. So we will never need 1,000 validators program or something like that. Just not necessary here in this case. So if we have two of these validators, one collects transactions, produces a block, and just sends it to the other one. That one will include the block and produce its own afterwards. And they will send block confirmations to layer one. So that's basically all there is. And as I said before, we don't interfere with the fee model of these sidechains. So if you want to have a feeless sidechain, fine, as long as you pay for the confirmation of the blocks on the layer one, that's fine for us. Or you can have your own native token on these sidechains, whatever. And now these sidechains, the really nice thing here for today's Sub0 Substrate developer conference, these sidechains are Substrate pallet compatible. So we actually wrapped the runtime that you know from Substrate into an enclave, but on the inside of the runtime, everything looks exactly the same. So you can, whatever pallets you have developed for Substrate, you can build sidechains made up of these modules, and that's exactly what we will do later in this workshop with a very simple pallet. Now, if we talk about enterprise use cases, here it is very important that companies can actually define in which jurisdiction the machines are operated. And we can, with sidechains, support permissioned operation because it's for the sidechain developers to define the model of permissioning, unpermissioning, authorizations, and so on, or incentivization in the terms of unpermissioned networks. So this is kind of an added nice feature that you can choose where the machines would actually be located. Okay, but now let's get a little practical. Today we will announce our collaboration with the IUNA network. That's another Web3 grant receiver, and they focus on, well, decentralized game engines and kind of virtual property inside games. And kind of NFTs you can use with these games. Today we will show a very, very simple example. We will play the rock, paper, scissors game. Now, you may be aware that the game actually, so you choose your weapon, rock, paper, or scissors, and the two people who play choose at the same time, so that you don't know what the other chooses, because then it would be easy to just select the other one, which would make you win. And in a blockchain context, as all this happens asynchronously, this is actually a nice case for confidentiality, because you want to commit to a weapon, but you don't want the other to see it before the other one has chosen his weapon. Now, obviously, there are other technical solutions for that than trusted execution environments, a lot simpler ones, but still it's a nice showcase. And before we go into the code, I would like to tell you a bit more about the architecture and what actually Integritee can bring to Iuna in this case. So one day, I'm very optimistic, very soon Integritee will have a parachain. Now, if we have a parachain, we can actually be kind of a early stage for teams who don't have a parachain yet. So Iuna maybe doesn't have a parachain yet, so they can deploy whatever they have in mind as a sidechain on our parachain until they have the parachain. But for us, it works either way. So either they can have their own parachain, which we can interoperate with, or they just have a sidechain. Yeah. Now, the actual game engine here will be on the sidechain, because we want this to be scalable. We want a really big number of people to be able to play this game at the same time. So here is this pallet, rock, paper, scissors. That's what builds what is the main business logic of the sidechain of Iuna here. Now this sidechain will use the pallet T-Rex. T-Rex is the T registry of the Integritee parachain. That's where you send your remote attestation quote from Intel Attestation Services to be verified. And they might have some data, some properties, NFTs, maybe game rankings or whatever on some other chain, some other parachain of the same system. Or as long as it is a substrate-based chain, we can actually trustlessly interface it, because we have a light client built into our sidechain, so you can trustlessly read state from other substrate-based chains. Now, the players, they don't need to send on-chain layer 1 transactions, as this is direct invocation here. So they just open a WebSocket to one of the sidechain validators, and they interact directly through a JSON RPC interface, which is very closely related to the one you know from Substrate nodes. So yeah, this is basically how this will be. And in the demo here that we show today, there will only be the Iuna sidechain and the Integritee parachain, which in our case here will be a standalone node in dev mode. Okay, so let's jump into the code. So we have two main repositories that you need to touch if you want to do that. So we have this pallet. We have this pallet rock, paper, scissors, which comes from Iuna, and we have the Integritee framework. Now the Integritee framework has this repo SGX runtime, and that's nothing else than the wrapper of a Substrate runtime into SGX. It patches a few of the Substrate pallets. We will see that in a minute. And here you will integrate now the pallet, the rock, paper, scissors pallet, and it will come to no surprise. You have in the TOML file here, you just need to integrate this pallet, and so this should be very familiar to Substrate developers. Here you have you need to implement the trait of that pallet. You add it to the construct runtime macro, and that's actually it. So now, so much for the runtime wrapper. That was easy. It's a single pallet with not too many requirements. And now we go to the worker, and the worker is the repository which actually builds into the service which will run an enclave on an SGX machine. So this can be either an off-chain worker with indirect invocation, or it can be a sidechain validator. Now, Again, we have a dependency on that pallet. Of course, we have the SPIO and the externalities pallets, which we had to patch in order to execute the runtime in SGX. And then we just do a few, well, we have to adjust the state transition function. So the STF crate in the worker directory is actually where your business logic lies. How it's kind of the glue code around your pallet or around whatever you want to use as your business logic. So in our case, we have a Rust CLI client. We don't need to go into too much detail, but this just uses Substrate API client to actually interact with either the node or the validateur. So we have a few commands that we can check out here. We have new game. So one of the players, the creator, will define who is my opponent. And that's it. You will just directly send a trusted call to the validateur, which says new game, and the new game will be created. Then we have choose, that is choose your weapon, choose rock, paper, or scissors. So each of the players chooses a weapon, and again we send a trusted call, this time RPS choose. And we sign that, obviously. Then we have reveal. Reveal is actually not necessary in our case, but the pallet supported it, because if you use salting of the weapon, then you have to first commit to a weapon and then to reveal the weapon when the other one has committed. Well, we didn't want to change the palette too much, so we just do it the same way. So we have the reveal function, but you don't need to bother about this. And then get game, this is now a getter, so that's not actually a state transition function. That's just a getter to see what is the state of the game. Are we in the middle of the game? Has the other chosen the weapon, or have I won or have I lost? And that's what we do here. Now, on the validateur side, we need a few helpers. So we, for example, have get game for. So here we read the storage of the pallet. So each pallet has its state, its storage variables, for example, all the games and the game identifiers and the game states. And we want to read that and provide the information to someone else. So we need to wrap that and not too fancy. And now the trusted calls that we expose for the users, we just have to define them in an enum. Let me show a little bit more here. So we have the enum trusted call, which can, well, do some balance magic, or here with our new palette, do a new game, choose, or reveal. And a little bit more, the trusted getter, which, for example, gives us the balance of an account or the nonce of an account, now also gives us the game state for a certain player. Okay, so now we need to wrap all this up. So we have the trusted getter is not that interesting, but the trusted call now. So this is an enum which we received through the RPC interface through a TLS connection. So that is an encrypted payload, which we decrypted. It is signed. We already verified the signature. That's all done by our framework. You don't need to care about this. Here we just map the call to the actual execution in the pallet. And so you see here, SGX runtime, we need to provide a origin. Because we verified the signature before, we can just generate the origin here, and then we will use the call of the enum of all the calls of the pallet, and we will call the new game dispatchable. And so this is actually a substrate code here. This should not, I mean, you don't actually, usually this is abstracted away from you through the runtime API in Substrate. And here it's a little bit more low level, but still, as you see, not too many lines of code. We also need to include the choose and the reveal function, and well, that's it. Now we have, initially I said we had the CLI client, and now this we can use for a demo on the Bash console. So what we will do is we will call the client to talk, pass the URL and the ports of the validator. And now, first, at Genesis, we don't have any balances here, but Alice is the sudo. And now Alice, or player 1 and player 2, they create new accounts. So that's just a new key pair. Alice as sudo will play the faucet and give them some balance. And then Alice actually starts a new game against Bob. So actually here it's not Alice, it's kind of player 1 and player 2, but well, never mind. So we call trusted, which means we call into the state transition function, and we call directly. So we call not through the blockchain indirectly, but we call directly to the sidechain validator. We need to supply the MR enclave that we want to talk to, because that's kind of the security check that only the correct code can execute that in the end. Alice chooses her weapon. You have direct here. Bob chooses his weapon. And then we have the reveal phase, which, as I explained, is not actually necessary here for the gameplay. And then we query the result. So that's basically it. I think there's not much more here. So I will now live demonstrate. We have a Substrate node, which has the T-Rex pallet in it. So that's our Integritee node. It's a standalone blockchain with just this trusted execution registry pallet in it. We start that, and it should be producing blocks. Yes, block 1. And now we start the sidechain validator. And now you will see, as I have a little bit of debug information here, first the enclave generates an account on the blockchain. Then Alice will, or a faucet will send some funds to the enclave's wallet. And then the enclave will query remote attestation at Intel Attestation Services. That's what happens now here with register the enclave, and send that to the blockchain. And that has now happened, and we are now producing sidechain blocks. And you see already here in this example, we are producing more or less 3 blocks per second, whereas we have 6 seconds per block on the layer 1. Well, in a local example, that might not be super impressive, but still, I mean, it's a lot faster than what we are used to. And now this will be very quick because we have such short block times. So the demo will run very, very quickly, and we will see what it actually does. So you see, we are talking to the node where we query the URL of the validator, and we will talk to the validator over another port here. We know the MR enclave, so we know that it's verified. So that's the remote attestation side. And Alice first sets the initial balances. That's not super interesting. Alice starts that new game. So this is submitted, and it is in sidechain block such and such. Alice chooses her weapon. Bob chooses paper. So Alice rock, Bob paper. So who will win? Alice reveals, Bob reveals, and the result is, well, Bob wins because paper wins against rock. And it doesn't make too much sense to play it again, because they will choose the same weapons. We didn't. We were not playful enough to do a different demo than that. All right, so I think there might be quite a few questions. So I'd like to take some of these questions. I do have, however, a little bit more in the direction of maybe let me do that first. So I present this. Now the question that we get very often is, well, okay, this is now running, but where can I get such an SGX machine? Now, SGX is actually commodity hardware. It's a feature of all the CPUs since a few years, but that's not enough, because the motherboard also needs to support that, and it needs to be enabled in the BIOS, which is not standard, and so it's a little bit tricky to choose the hardware, because even Intel is not very good in telling you which hardware you should buy and be sure that it will work. So we're not advertising here. I'm just telling you what works for us. So we have on-premises here. We have an Intel Xeon, a Dell server, with where we just know which CPU, which version of the server, and it will work. Or what you can do if you don't want to have your own hardware or housing or something like that, there are bare metal providers. So there is IBM, there is not too many, but OVH is one, and they have a bare metal cloud where you can rent an SGX enabled machine for around €100 per month. What you need is you need to obtain a commercial license with Intel. So not the users, but the ones who want to operate the Ts, they need a commercial license. This commercial license is for free, but you need to be a legal entity and not be affiliated with the army or something like that. And we have a set of Ansible scripts ready for you to set up this machine, because it's a little tricky. The versions of different tools need to really be aligned. It's not a very simple thing to set up. And then you just run a handful of validators, and that's basically it. And I mean, Integritee is happy to support you with that, but you're entirely free to do that on your own. You're also free to just take our code, build our pallet into your chain, and use exactly the same technology. So it's all Apache 2 license. We don't force anyone to be locked into our parachain. We just believe that the convenience is a lot better for teams to actually use our parachain. All right. Time for questions, I think.
Awesome. Thank you so much. It was really, really interesting talk. Just confidentiality is something that we usually never see in many of the blockchains, and just being able to handle some confidential transactions and some data privacy here, it's really, really cool. There's one question here from the audience. So it's like, it says, can the calling application verify the remote attestation of the RPC node it is connected to?
Yes, it uses, so the client, no, let me start. The SGX machine has to supply remote attestation in order to be registered on the on-chain registry on our parachain. The client doesn't see the entire certificate from Intel and doesn't need to check it, because the blockchain actually did. The Pallet has all the logic to verify that certificate and parse all the details of these reports. For example, in there you see if the latest security patch has been applied to that SGX machine and so on. Now the client just needs a trust. A connection to the blockchain it trusts. So usually we would recommend. We heard it yesterday about the Light client in the browser. So the client should use a Light client to really have a trustless read on that remote attestation registry. In there you see the URL of the validator you will be talking to. So indirectly, yes, the client can verify remote attestation by just looking up our registry. So that's actually the added value of the Integritee parachain, that you can do that.
Awesome, thank you. Really good answer. I was also thinking, like, you just mentioned that you are using the Intel SGX enclave, but is there any way or any plans to probably like expand to ARM enclaves or something more? Yeah,
Absolutely.
probably that could be cheaper.
Well, cheaper is not our biggest concern, actually. It's more about the trust, because we want to build unstoppable applications, right? So we don't want over the long run have a manufacturer play such a central role. We think for now this is a very good middle ground in terms of security and trust, because we can do a lot more already in terms of a lot of good in terms of confidentiality, and still have a reasonable decentralization. But definitely hardware diversification is a topic for us. We have played with ARM Trust Zone. The problem with ARM Trust Zone is that it hasn't been. It has a different application model, actually, because remote attestation is not something they feature. So the manufacturers are not able to remotely attest ARM Trust Zone devices. ARM Trust Zone devices are just there to convince the holder, the owner of that hardware, that something happens in a trusted execution environment, not someone else. So here Intel is pretty unique still, or is unique in offering that. What we would like to work on in the midterm is bringing open source enclaves to our system. So there are initiatives, academic initiatives like Keystone, for example, which is an open source RISC-V design. Obviously, you cannot do super duper number crunching, heavy duty computation on such a device. But let's say light applications could be run on such a device. And then we would have something which is really auditable by peer review, where we still need a certain trust in the manufacturer, but at least we can make them accountable for it, and see if they actually what they produce corresponds to the design, to the open source design.
Awesome. Yeah, thank you. That would be really interesting, because yeah, at the end, just depending on one technology will centralize all the
Exactly,
older chain,
exactly.
right?
There is a caveat all here, because hardware diversification can be good and bad here. So if you want to have one use case and 3 different T's to support it, then that actually weakens the guarantees in terms of confidentiality. With integrity, it's good. So the integrity increases if you can diversify, but the confidentiality guarantees, they decrease, because now it only takes one of these technologies to leak a secret. So we have 3 times higher risk of data leaks. So one needs to be careful there. Diversification is a very good thing. We strive for that, but it has its downsides as well.
Yeah, really good point. Yeah, one step at a time, right? So
Exactly.
yeah,
Exactly.
there's another question here. I don't know how familiar you are like with Fala and Hala. Like basically, if you can, I mean, they are asking if you know, like how different is integrity from Fala.
We actually were in contact with Fala very early on, and we even exchanged some snippets of code mutually. So we're on a good basis there. The difference that I see is that Fala has an unpermissioned model where you can run SGX devices and earn tokens for that. But that means that in the Fala ecosystem, the Fala token plays a role even for all the dApps which will be on top deployed on top of it. So actually there again, you have a certain competition between different dApps because dApps are not caring for their own infrastructure. In our case, we are really just this middleware that enables others to run infrastructure. But a dApp like CryptoKitties would need to care for their own infrastructure. Either they operate it themselves or they have an incentive model for others to run it. But it's dApp per dApp, the responsibility for infrastructure, which is not the case for Fala. So it's fundamentally different in what kind of economic design and also in terms of scalability. It's fundamentally different because we have sidechains, which are a different order of magnitude in scalability.
Okay, thank you. Yeah, that sounds really good. So there's another question that also relates to the previous question. It's basically like your technology, as we were discussing, it's mainly designed for Intel. So how much changes do you need to do, like to support MAD or any other? Would you really need to rewrite all of your code because it's low level, or?
Yes, we use a very low-level SDK. So we build on the Tclave SDK, which is a Rust wrapper around the C SDK from Intel, so that's very low level. But anyway, I mean, we can reuse a lot still in terms of design, architecture, and so on. But in terms of pure code base, there will be quite a bit of refactoring if we change the underlying technology, for sure.
Okay, thank you. Yeah, makes total sense. So yeah, thanks, Alain. It was really interesting and great talk. Just getting to know more about Integritee.